So happy snow day, everybody. So in today's lesson, I'm going to be recapping some of the skills in measuring and performing calculations that we would have talked about in previous science courses, but that will be critical when you're solving any kind of numerical problems in grade 12 chemistry. So just to recap some of those ideas, it's important whenever you're indicating a measurement that you include the value of that measurement, the number, to a certain number of significant digits, and then you include a unit that represents the dimension you're trying to describe. So there are three key processes that need to be done or performed or sort of thought about while you're working through problems. You need to make sure that any answers, any responses that you're given are rounded to the appropriate number of significant digits. You need to make sure that prior to commencing the solving of a problem that you've converted to the appropriate dimensions that are, the dimensions that are appropriate for that formula, and that you have the ability to isolate and solve for a particular variable in a given formula. So many of you may not need to review these ideas, and that's perfectly okay. You can go straight towards the worksheets or not at all. We will have a quiz on this, and so I want to cover all the bases and make sure that I'm providing you with all with a quick recap of this. So Sig Figs, I usually start out by having a conversation with students about something like this. So I would say, all right, well, so what's the difference between if I said 2 meters, and pardon my scribble here, versus if I said 2.00 meters, right? So many students, their first time through, will say that these are identical. They mean the same thing. And from a numerical perspective, perhaps that's true, but not from a measurement perspective. So as soon as you add these 2 decimal points, what you're indicating to the reader is that you have greater confidence in the accuracy of this measurement to the second decimal place. So this number up here, the 2 meters, well, that could mean, 2.1. It could mean 2.00, but without any extra information, we don't really know what happens after the ones. We don't know to the first or second decimal place. We only know that it rounds to 2. So whenever you're representing a measurement, the number of decimal places that you choose to round to gives the reader an indication of the degree of confidence that you have in that measurement, which is why it's really important for you to be concerned about that. Usually I'll say, well, let's take a look at the measurements that were used in calculating a given dimension. So in this one, density, we know density gets measured by taking the mass of an object and its volume as well. And so I know that, for example, in our class, our electronic balance will measure to 2 decimal places. And if we were being, pretty sloppy about it, we might be confident to 1 decimal place with our graduated cylinder, or 10 milliliter graduated cylinder. And so if we analyze the calculation for density, we have a value that has 2 decimal places being divided by one that has 1 decimal place. And the crude calculation gives us a value that has a whole whack more decimal places. And so that really, we need to think about whether that makes sense, whether that's reasonable. It's not reasonable to have a value that is calculated that comes from values that are far less accurate. So we need to make sure that we round appropriately, and that's where significant digits and the rules related to significant digits come into play. And so you'll find on on Google Classroom, you'll find an outline of the worksheets reminding you of some of those rules. So I'd like you to review those, and feel free to come to class with any questions where you're not sure of why a particular response was what it was, or if you simply need extra practice. So given that you all had just finished grade 12 functions, advanced functions, I don't feel like I need to go through how to solve and isolate a particular variable. We're just going to apply the laws of algebra for that, but please do work through the practice worksheet that I've included for you. They get progressively more difficult, so you may feel like you can skip a few of the first formulas and questions, and then kind of skip ahead to the last ones. But make sure that you do exercise your brain in that way, because that is an expected skill that you have coming into grade 12 chemistry. So converting units, this is the one that students tend to struggle with the most, but it is an important prerequisite. In fact, there are courses in university, particularly in engineering, where the sole purpose of the course is to teach you how to perform dimensional analysis and work through some sort of wacky unit conversions, and the basis for it is the process that I'm going to review with you today. Of course, with simple conversions, you may not need to use dimensional analysis, so I'm showing you these simple examples merely as a refresher, although perhaps converting from kilometers to meters may not be, it might not be necessary for you to go through the motions of dimensional analysis. But as the questions become more complex, the process becomes more important. So an example that I'll often use with students is to say, well, you can probably guess what 2x equals 8 is using guess and check, using a simpler sort of method. But you get to the point where, the rules of algebra make it far more efficient. So like if I had 2.873x equals 8.93, well, you could kind of guess and check your way to get a certain number of decimal places, but essentially the rules of algebra will make the solving of this far more efficient than any kind of guess and check method. Okay, back to dimensional analysis. So again, may not be necessary for simple conversions, but for more complex ones that we will see in this course, the method will prove very useful. So just to remind you of some key ideas. So what you may want to have, and I'm just going to quickly flip to my website. And remind you what you'll see when you go there. Let's just let it load. What you'll see is over here, unit conversion factors. And if you click on that link, it will bring you to a document with all of them on it. And of course, it's not all showing up on this screen. It's taking a minute to load, but that should seem familiar to you based on previous science courses. So it will tell you what each prefix indicates in terms of powers of 10. So what this is indicating to me, say for example, is that 1 kilo, and then my base unit, so kilometer, kilo, second, kilogram, whatever, is equal to 10 to the 3 of my base unit. So 10 to the 3 if we're using grams. Here, if this is kilograms, 1 kilogram is equal to 10 to the power of 3 grams. And so on and so forth. So the 1 is really expected to go with the dimension that has this prefix. Okay, back to the lesson. So just to remind you of the setup, I'm going to start with a simple one and then move into a more complex one. So 2.5 kilometers, and I want to convert that to meters. So I'm going to write out the unit that I have. Oopsies. 2.5 kilometers, and I know that I want to eliminate kilometers and end up with meters at the end. So in order to cancel those, they have to be on opposite sides of a fraction. So kilometers up here divided by kilometers will result in 1 whole. And I want to end up with meters, so my meters are going to be in the numerator. And now it's time for me to indicate what the relationship is between these units. And so, use reasoning skills to help you with this. I know that 1 kilometer is equal to 1,000 meters, or 10 to the power of 3 meters, however you choose to write that out. And so now I like to do this just because it makes me feel more confident about my answer. Kilometers are canceled out, and I end up with units of meters that result. And of course we know that this is going to give us 2,500 meters. So that is an illustration of the process. And the process is based on just the cancellation of units using a factor that relates those two units. Ooh, messy. Okay, on to a harder example. Okay, so in this case, I have units that are rates. So I see that I'm looking at speed, in this case kilometers per hour to meters per second. And so in this case, whenever I have units that are a rate, I tend to write the unit as a fraction in fraction form, because helps me to see the cancellation a little bit better. I'm going to switch this to blue. So, for instance, I have 55 kilometers per hour. So I'm going to write this as kilometers divided by hours. And eventually, at the end of all of this, I want to end up with meters per second, which means that I need to get rid of my kilometers and I need to get rid of my hours as well. So I'm going to start by positioning my units appropriately for cancellation. And I know I need to get rid of kilometers, and so my kilometers are going to have to be on the opposite side of the fraction so that they cancel. And the unit that I'm seeking is meters, so meters will have to remain in the numerator and not be canceled out. So now I'm going to write out my conversion factors here. I know that 1 kilometer is equal to 10 to the power of 3, or 1,000 meters. And so just to kind of keep track of my units, let's cancel those kilometers out. But now I have hours, and I don't want hours. I want my rate to be per second. And so my hours, in order to eliminate them, to cancel them out, they have to be on the opposite side of the fraction compared to where they are. So hours need to go up here. And I want to keep it with per second. And so looking at the relationship between these two, I know 1 hour has 60 minutes, and every minute has 60 seconds. So this will give me 36. Oh, I can't squeeze it in. 3,600. Ooh, there we go. Seconds. It's messy. Sorry about that. And that will allow me to cancel out my hours. And so I'm left with units of meters divided by seconds. In other words, meters per second. And so if I were to work all of that out, I get approximately 15 meters per second. Hopefully I didn't mess that up. Now, some of you may be saying, well, yeah, but I can just sort of memorize a unit conversion factor, and for sure that's efficient. But remember that, particularly in engineering, you're going to see some wacky units, and so the skill of converting from one unit to another is going to be really important, and you may not have a direct conversion factor for all of them. So the last little bit of this that I want to discuss with you is when you have to do a unit conversion that involves any kind of dimension that has an exponent. So for instance, meters squared, centimeters squared, or cubic units, and so on and so forth. It's not as straightforward as some of the other conversions. It's not a direct conversion. So I'm going to illustrate for you how to go about this. So the first thing that you want to do is set things up as you normally would, but without the squared units. And you would set up your unit conversion factors as before. So I know that 1 meter, in 1 meter there are 100 centimeters. Or if you were using the chart, this would look a little bit differently. I would have, 1 centimeter is 10 to the negative 2 meters. So here we go. So I've set it up, but in doing this, I'll be left with a meter, right? Because meters squared divided by meters would leave me with a meter up here. So I need to take, and this is the new part, so I need to take that into account. So how do I turn a meter into a meter squared? Well, I square it. But remember, whatever I do to one part, I have to do to the other. So I need to square both parts of this fraction. So that is the new part. So let's see what we end up with after we do that exercise. So instead now I'm looking at still my 2.5 square meters. Ooh, a little bit messy. But instead, this would be 10 to the power of 2, right? That's what 100 is. Sorry folks, I just got interrupted by wonderful Mr. Benoit. Here we go, let's carry on. So I'm going to work this out. So 10 squared and then squared. If you're remembering your exponent laws, then we just multiply that. So really now I have a factor of 10 to the power of 4. Of course, you don't have to do this in scientific notation, but for me, I find it easier. But now I also have to square my unit. So now instead of having centimeters, I have square centimeters, centimeters squared. Here we go. Now, of course, you know, one squared is just going to give me 1. And meters squared now. So now I have meters squared, which is, you know, going to allow me to cancel out this initial unit of meters squared. And so I just kind of carry on as per the usual. Square meters canceled, and now I have centimeters squared that remain. So now I'm going to multiply my 2.5 times 10 to the power of 4, and that's going to allow me to have the correctly converted value. The nice thing about converting my powers of 10 to scientific notation is that I already have this kind of set up. So 2.5 times 10 to the power of 4, whoa, this is messy, square centimeters. Okay, so if you were working with you know, cubic centimeters, then instead we'd have to cube the units here and cube the factors as well. But the process, I think, is fairly straightforward. I'm going to set you off with a few different worksheets today to have to work through. Again, skip what you feel you are comfortable with already, but you will be evaluated on all of these concepts on our scientific inquiry skills quiz later on this week.